right, welcome to the replay. Today we're going to do a real quick, fast scope. I'm going to show you, hey, Rap 43, welcome. I'm going to show you a pretty cool little demo involving a Van de Graaff generator. So what you're seeing right now is on top of the Van de Graaff generator, there's what's called an electric pom-pom. It's just some small, light strings. Let me turn this off for a second. All right, welcome John, welcome Diane, welcome Mama Vamp. My name is Joe McCullough. Let me turn. And today I'm going to show you a quick demo involving a Van de Graaff generator. Did we miss it? No, you did not miss it. I'm going to see if I can show you this and be in the screen at the same time. So this is a Van de Graaff generator. What this is there's a little belt here and it's carrying, hey, check out my reflection. Do something with anti-gravity. So this is carrying electrons up to this metal sphere. The metal sphere is getting a huge amount of negative charge. Awesome, I have a 9 and 7-year-old watching. Hey, welcome John, welcome 9 and 7-year-olds. My name's Joe, I have one in my class, Van de Graaff generators, I love it. So what I'm gonna do is turn this on and first show you what's happening with the strings. Key thing here to know is like charges repel. So when I turn on the Van de Graaff generator, this metal sphere is getting a huge amount of negative charge, and the negative charge, even though this is an insulating base, the electric field is great enough that the charge will actually flow through it. All of the strings are going to become the same charge, and what you're going to see are the strings repelling each other. So let me turn this on and show you. So the strings are standing up right now because the strings repel each other because they're all negatively charged. And when I shut this down, what happens is these strings quickly lose charge to the air. Things that are charged do not stay charged. It's losing charge to the air, going back down. Then if I touch this, I'll leak out most of the charge. Let me take this away and try and show you the actual electrons transferring from one to another. Now, you're not going to be able to see the electrons, but I'll explain exactly what you're seeing. See how well we can see this? Can people there see the purple going from one to the other? Will your hair stand up if you get near it? The answer is yes, but it depends upon how light the hair is, and it doesn't always work. Now, you can also do this with your finger, and I've done this a lot. You don't want to use your fingertip because your fingertip has lots of nerve endings on it. Your knuckle, not as many. So let me see if I can do this. I don't want to get my iPhone too close. I don't want it to arc to the phone. Bring this back a bit. Ow! This is one way of waking up in the morning. Now, quick question. What do you think you're seeing? You can see a purple arc going from one to the other. My new hero, thank you. But some interesting science is you are not seeing electrons. Electrons are way too small to see. What you're seeing is the path the electrons take when they're going from the Van de Graaff generator to the sphere. And what happens is as the electrons travel through the air, they excite the air molecules. And when the air molecules de-excite, they emit light. And what you're seeing is the light emitted by the air as the electrons go through it. How many volts? Now, it depends upon the exact Van de Graaff generator. You're talking on the order of maybe 5,000 or 10,000 volts. Sounds like a tremendous amount, but there's not a lot of current associated with that. What I want to try and show you is a pretty cool demo where you can get a piece of string, or in this case, sorry, a piece of fur bouncing back and forth. So let me see if I can get this to work. It doesn't always work, but it's pretty cool. Can we use that? I love you guys on Periscope. You crack me up. Okay, I'm going to try and zoom in a bit. Now, I'm either going to get this to work or it's going to shock me. Can you guys see that bouncing back and forth? So this is my elbow you're seeing, and you're seeing a piece of fur bounce back and forth between the Van de Graaff generator and my elbow. Woo! Pretty cool, huh? Now I'll explain this in 1 second. Now you can see this, actually this is cool too. This is bouncing back and forth between the sphere and the Van de Graaff generator. So why is it bouncing back and forth? Great question. I'm going to explain that in 1 minute. Real quick intro for those of you just joining. My name is Joe McCullough. I'm the physics department chair at Cabrillo College, and I have been on a mission to provide daily doses of dopamine through education, entertainment, and inspiration. Today, tomorrow, and Thursday, I'm going to be showing you some pretty cool physics demos. So a couple quick things, and then I'll show you this demo again. One, for those of you who have never taken any science, atoms, for the most part, any atom you see consists of 3 main particles: protons, neutrons, and electrons. Protons are positively charged, electrons are negatively charged, neutrons have no charge. 2 key facts. 1, opposite charges attract, so a positive and a negative charges will attract, and like charges repel. So 2 negative charges or 2 positive charges will repel each other. And then the other thing you need to know is force depends upon distance. The closer together 2 charges are, the stronger the force. The farther apart they are, the weaker the force. And it actually is an inverse square law, which means the force depends upon 1 over the radius squared. What that means is as charges get farther apart, the force gets weaker, but weaker not linearly, but as a square of the distance, inverse square. So what happens why does the fur bounce back and forth? Give you a quick little explanation. So right now, this Van de Graaff generator, when I turn it on, is building up a huge amount of negative charge. What happens with this piece of fur is one side of the fur, the side closest to it, becomes positively charged. The side farthest away becomes negatively charged. And since the positive charges are closer to the Van de Graaff generator, the attractive force is stronger than the repulsive force. So the fur comes and it hits the Van de Graaff generator. Once it does, now some of the negative charge from the Van de Graaff generator transfers onto the fur. So now the fur is negative, the Van de Graaff generator is negative, it repels. Then when it hits my arm or elbow, I am a conductor, and so some of the excess charge gets dumped onto my body, and now the fur is neutral again. And now that the fur is neutral, it gets polarized, meaning one side gets positive, one side gets negative. Because the positive side is closer, the attractive force is stronger, it gets attracted. Once it hits the Van de Graaff generator, it picks up some negative charge, it gets repelled, and then the whole thing repeats back and forth and on and on and on. So let me see if I can do this for you one more time without shocking myself too badly. So here's a piece of fur. Ouch! All right. Where is that? Trying to move it so you can see it. All right, let me tilt this down a bit. All right, I'm having some technical difficulties with the camera here. So let me just actually turn this one more time. Oops. Woo! All right, can you see that fur bouncing back and forth between this and my elbow? Again, what's happening is when the fur is near the Van de Graaff generator, the charges become polarized. The side closest to the Van de Graaff generator becomes positively charged, so it gets attracted to the Van de Graaff. Once it hits it, then it gets negatively charged, so it repels. And then once it hits my elbow, it dumps all of that negative charge onto me, and the whole process repeats itself. Woo! Okay, one more quick little time for those of you tuning in late. I'm going to show you some of that purple. Wow, now it's going really well. Does it blend? Okay. So this, what you're seeing, is basically lightning on a smaller scale. Again, you cannot see electrons because they're way too small to see, but what you're seeing is the path that the electrons take through the air, and when they travel through the air, they excite the air molecules, and when the air molecules de-excite, they emit light, and in this case, it's a bluish purple light. And I'll show you one more demo. So what I have on top of the Van de Graaff generator is, it's called an electric pom-pom. It's basically just very light strings. And when you turn the, hey, check out, I can talk into the, hey, when you turn on the Van de Graaff generator, sorry, I've been teaching for 9 straight hours. I'm exhausted, I'm about to go home. When you turn on the Van de Graaff generator, these strings will pick up negative charge. Since all the strings are negatively charged, like charges repel, you'll see them stand straight up. And when I bring this near, you'll see them dance, because once the Van de Graaff discharges, now there's less negative charge, these strings drop. Woo! Okay, that's it for today. A real quick scope talking about a little bit of electricity. Tomorrow I'm going to show you another cool physics demo. I think the demo I'm going to show tomorrow is how you can use the air in the room to crush an aluminum can. And this is a great demo because you can do this at home. All you need is an aluminum can, a little bit of water, a stove, a burner, and maybe some ice. So tune in tomorrow. What happens if you spray water in the air? Ooh, I don't have a water bottle, but water is a polar molecule. So what'll happen is the water will get attracted to the Van de Graaff generator because the positive side will turn towards the Van de Graaff generator. So the positive side will be slightly closer to the negative charge from the Van de Graaff generator than the negative side. The attractive force will be a little bit stronger. Great question. Before I leave, any last minute questions? Cool. Thank you so much for joining in. If you want to check me out tomorrow and future scopes, please swipe from left to right on an iPhone or straight up on an Android and hit follow. And if you feel like people might enjoy this, please also consider sharing it. Thank you so much. This is Joe McCullough signing out for today. Hope you have a wonderful evening.